Thank you very much for coming. I'm delighted to have this opportunity. So I'm going to describe a geometric PDE approach to what will sound like an algebra topological problem. And this will be a general talk, so I've slid a lot of the technicalities under the rug, but I would be happy to answer any questions you have during the talk about details. So let me begin with the introduction. What are the questions and the objects we'll be looking at? So we start with X, a rational homogeneous variety. And I'll give you a toy example to hold in your hand as we go through the talk. So this is a complex projective algebraic variety. X sitting inside some complex projective vector space, and it's homogeneous under a group that we'll assume to be connected, complex linear algebraic group. Which you can think of as sitting inside the endomorphisms, the automorphisms of V. Okay. So the example you can think about as we go through the talk is the case that X is the Grassmannian of K-planes in N space. And then this embeds as an algebraic variety via the Plucker embedding, which goes into the projectivization of the kth exterior power of complex N space. Okay, so we're looking at all the k-dimensional linear subspaces in a complex space. And our group G is just the image of the natural embedding of the special linear group. This acts on Cn, that extends to an action on V. This sits inside SLV. Okay. So I want to, throughout, fix an origin, a reference point in our variety, and let P be the stabilizer of that point in the group G, so that we can write X as a homogeneous space, G mod P. All right, now sitting inside any one of these rational homogeneous varieties are a distinguished class of subvarieties. These are the Schubert varieties. If you haven't thought about these in a while, I'm not going to remind you of the proper definition. I'm just going to tell you why they're important and give you some examples to hold in your hand for the talk. So one of the reasons they're important is a result due to Borel in 1954 that asserts that the classes, the homology classes of the Schubert varieties, S in X, form a free additive basis. Basis of the integer homology. Okay. And they play an essential role when studying the geometry of rational homogeneous varieties. You probably also know that they play a significant role in representation theory and combinatorics. So the running example to keep in mind for this talk are the Schubert classes sigma sub lambda of the Grassmannian of K-planes in N space. These are indexed by increasing sequences of length k bounded between 0 and n minus k. And to describe the Schubert variety representing one of these classes, we need to fix a flag of linear subspaces. So this would be F1, F2, and so on, all the way up to Fn, which is Cn. Okay, so the dimension of F1 is 1, one-dimensional linear subspace, two-dimensional linear subspace, and so on. And then the corresponding Schubert variety associated to that flag and indexed by lambda is the set of all k-planes with the property that they have this non-generic intersection with plus A greater than or equal to B. Get my indices right? Yeah. For all A from 1 to k. And then the dimension of one of these S lambdas is just the sum of the lambda A's. Okay. And one thing you can check is that the homology class does not depend on the choice of flag. And the reason for that is our group in this case is the special linear group. Any two flags are congruent under the special linear group, which is path connected. So any two varieties given by different flags but the same index set will be homologous to each other, congruent under the group action. Right. So some of the questions I'd like to discuss related to Schubert varieties are the following. So the first is, aside from the Schubert varieties themselves, and I'll consider anything congruent to a Schubert variety a Schubert variety. Okay, we're in a homogeneous space. We shouldn't distinguish two objects that differ under the group action. So let's just call that this guy. Aside from the Schubert varieties, what are the algebraic representatives, y contained in X, of the Schubert class? So just as an example of when there might easily be seen to exist others, again, in the Grassmannian of k-planes in n space, the Schubert variety consisting of all k-planes that have a non-trivial intersection with the n minus k subspace. This is a singular hyperplane section. Of X, of the Grassmannian. And Bertini's theorem tells me that if I take that hyperplane and jiggle it a little bit, I get a smooth intersection, and that will be a smooth algebraic representative of the class. Now, since the Schubert variety itself is singular, that's clearly a distinct algebraic representative. All such smooth representatives? No, I don't believe it does. Okay, so just as a over here, that Joshkin in 2010 identified the rigid classes in the Grassmannian of K-planes and n-spaces. So these are the Schubert classes for which the Schubert varieties are the only algebraic representatives. And I realize I forgot to mention that much of this is joint work with either Dennis Tay or Zet Joshkin, which we'll be talking about today. Okay. Many of them. Many of them, I would say, rather than most. No, I'm sorry, I misspoke. No, I think, no, many of them, most of them are not rigid. Not rigid, I said that backwards. Okay, now, remember we discussed that hyperplane section, which is singular. Most Schubert varieties are singular, S-I-N-G-U-L. And in fact, S is, in some reasonable sense, the most singular algebraic representative of its homology class. Okay. So in connection with this observation,
that's for this S or for any single?
For any X and any S. So for any rational homogeneous variety and any, most Schubert varieties are singular, and they can be viewed as the most singular representative in that class. So there's a question that goes back to Borel and Haefliger in 1961, which asks which sigma can be represented by a smooth algebraic object, a smooth algebraic variety. Okay, so this is an interesting question. Right, from the Bertini example here, sometimes it's quite easy to dig these things up. Sometimes they don't exist in any reasonable sense. So there's work of Hartshorne, Rees, and Thomas from 1974, which, just to give you an example of how badly things can go wrong, where they show that the Schubert class indexed by 1, 3 can be written as the difference of two smooth objects, 14, 8, in the Grassmannian of two planes in 5 space, but cannot be smoothed. So this class admits no smooth algebraic representative. And then things can get even worse. The Schubert variety, Schubert class indexed by 1, 3, 3 in the Grassmannian of 3 planes in 6 space cannot be represented by any integer linear combination. Of smooth varieties. So I'm not familiar with their proof. They use topological methods of Tom to show that this is true. This is the case. Is that, so again, in 2010, Zet gave a nearly sharp description of the smoothable classes in the Grassmannians. Okay. And by nearly sharp, I mean there was just a small handful of classes that he couldn't sufficiently nail down. And the description is very clean. It's in terms of these increasing sequences lambda. It's very explicit. So remarkably, there's a PDE approach to this, to these questions. Well, if you allow me to apply a slight bait and switch. There's a theorem independently proved by Maria Walters in her thesis for the Grassmannian in 1997, and by Robert Bryant for general X in 2001, which states that if X is co-minuscule, and I'll define co-minuscule in a moment, then your algebraic variety is homologous to a multiple of a Schubert variety if and only if Y is a solution of the Schur differential system. And I'll call that R sub sigma. Okay? No, X is my rational homogeneous variety, and Y is the subvariety of X that might be representing a Schubert class or its multiple. Okay, so I need to define co-minuscule and the Schur differential system. Let me just say briefly that this theorem is a consequence of Costin's work on Lie algebraic homology.
So you're saying Y is non-singular here?
Y could be singular.
Okay.
That's okay. So let me just introduce another definition first, which is that I will say that the class is Schur rigid if the Schubert varieties themselves representing that class are the only irreducible algebraic solutions. Of the Schur system. Okay, so let me start with co-minuscule. The following are equivalent. Our homogeneous variety, xg mod p, is co-minuscule. X admits the structure of a Hermitian symmetric space. Okay. I favor the language co-minuscule for this talk because I'm not going to take advantage of the metric structure. But these are basically Hermitian symmetric spaces. Or if you like, the isotropy action of P on the tangent space at our origin is irreducible. Okay? So remember, P is the stabilizer of the origin, so it acts on the tangent space, and there are no invariant, non-trivial invariant subspaces. So the irreducible co-minuscule varieties have been classified. You're familiar with most, if not all of them. So our running example of the Grassmannian is included. We also get quadric hypersurfaces, Lagrangian Grassmannians, spinor varieties. This is one of the two connected components of the n-dimensional isotropic linear spaces in C2n for a symmetric, non-degenerate symmetric form.
So the Cayley plane that was underneath that was your doing?
Yes, yes, oh yes, we'll talk about that, yeah. It's not a math talk without colors. Yeah. So these are the exceptional, or I'm sorry, these are the classical series. That's what I mean when I say classical. And then there are two exceptional cases. The Cayley plane, which is homogeneous with respect to the exceptional Lie group of rank 6, and the Freudenthal variety, which is exceptional with which is homogeneous with respect to the exceptional Lie group of rank 7. Simple Lie group of rank 7. So those are the objects that we're talking about from now on. If you like, you can continue just to think about the Grassmannian, but any one of those is fair game. Let's see. I think I'm over here now. Well. So now let me give you the definition of the differential system. It's very geometric. It's determined by the Schubert variety itself. And you can describe it as follows. So let's fix our class we want to study. And let's assume that it is of dimension d. And without loss of generality, we can suppose that O is a generic point. Okay. If it's not contained in S or it's not generic, just apply the group action until that is true. So I said that the stabilizer of O acts on the tangent space. Okay. So let it act on that tangent space. This will sweep out a subvariety in the Grassmannian of d-dimensional subspaces of the tangent space. And let's call that subvariety B. Okay. So we're going to take the tangent space and just push it around by the isotropy action. Okay. Now think about this Grassmannian as sitting inside a projective space by the Plucker embedding. And then if you do that, you can take the projective linear span of this object, its projective linear span inside this space, and re-intersect with the Grassmannian. So this will be a subvariety R, and these you can think of as the allowed tangent spaces for a solution passing through O. And then to get the full system, we just knock it around by the group action. So R sigma will be G applied to R, which now sits inside the Grassmann bundle on the tangent bundle. And then we say that a variety Y contained in X is a solution if the tangent space is contained in this subvariety for all, or this subbundle, for all generic smooth Y.
So you're assuming that Y is already algebraic?
Yes, I'm really only interested in algebraic solutions. Yeah. Well,
What kind of system of equations? Highly overdetermined?
yes, it's highly overdetermined, it's homogeneous, but you can lift it to a Pfaffian system. So it's entirely tractable. No, well, you know that the Schubert varieties are solutions. And so one thing you can do is, this is not obvious, but you can show that if there is a local complex analytic solution, then there is an algebraic solution. But that's a sort of a posteriori observation after you analyze this. So basically what we do to get this system is we take the tangent spaces to all Schubert varieties of a certain type at a good point, and those are the allowable tangent spaces for solutions. It's a messy definition, but the geometric idea is very simple. So let me just mention that this system has been studied by a number of people. So first, Maria Walters, as I mentioned, in 1997. And she looked at smooth Schubert varieties in Grassmannians and codimension, dimension or codimension? Codimension 2. S in Grassmannians of two planes. Robert Bryant looked at smooth Schubert varieties in Grassmannians and Lagrangian Grassmannians. Maximal linear subspaces in the classical X over there on the far board, and singular S in Grassmannians of low dimension or codimension. Okay. So the approach here to the smooth Schubert varieties was a bit ad hoc. In 2005, 2007, Jaehan Hong, 2007, studied the smooth Schubert S. Smooth Schubert varieties in arbitrary X, arbitrary cominuscule S, and identified all the rigid ones. Okay. It's a really nice argument. It's based on Costin's Lie algebraic homology, and informed the approach that Dennis and I took to the general problem. She also did some work with general S in the Grassmannian. Okay. So what I want to do for the rest of this talk is talk about this differential system. I want to talk about its rigidity, flexibility, and then some surprising superflexibility that we can observe. So let me start with rigidity. So this is the question: when are the Schubert varieties the only irreducible varieties that are homologous to a multiple of a Schubert class? And the theorem, which is joint with Dennis Tay, 2011, is a complete list of the sigma in the cominuscule X for which there exist first order obstructions to flexibility. So everything on the list is rigid.
I'm missing something. If you return a Schubert variety to a smooth one, as in your S up here, will it still satisfy the differential system?
If it's done with this sort of, if it's if the perturbation is so that it's homologous, then yes.
I see.
Right. Because anything that's homologous to a multiple of this will be a solution of the system. And that's if and only if. I mean, it's really an amazing consequence of Costin's work that you get this differential geometric characterization of this topological property. It's really, really beautiful. Okay, so I want to make a few remarks about this. So first, a priori, there may be higher order obstructions. So Hong's proof in the smooth case basically goes by this sort of argument where she identifies first order obstructions to flexibility and then uses a simple topological Bertini based argument to show that the others are flexible. And I'll talk about that a bit more later. Next, sigma is on the list. Sigma is sure rigid if and only if its Poincare dual is, which is surprising. And for those of you who like to think about these objects, you will know that there is a bijection between the homology of the Lagrangian Grassmannian and spinor variety, and this bijection preserves the list. This is observed a posteriori. It's not clear to me why this works. It's, the combinatorial data matches, basically.
How big is this list? How much bigger is this list than Justin's
So this list, it's a list of rigid objects, so it'll actually be a little bit smaller than his because he only lists, so these are things for which the only irreducible varieties of any multiple are the Schubert classes. And that would, I think, if I'm not being run amok by my dyslexia, that'll be contained inside Izette's list. And I don't know how to quantify how much bigger when they're finite sets. They're both described in the same language, so you could just run a comparison. I don't have Izette's characterization off the top of my head, though. Okay, let me just make a quick remark on the proof. It is by Eli Carton's exterior differential systems machinery. Okay, so as I alluded to before, you can lift this system to a Pfaffian system. It's a geometric overdetermined system, so it's ideally suited for Carton's machinery, and you just grind the crank. Okay? There is a fair amount of representation theory in this computation. Without representation theory, you couldn't do the computation. If you've ever tried to do an EDS computation in general, you know that while theoretically it can be done, they can become messy quite quickly. The representation theory plays an essential role in organizing the computation. And there's a very nice interplay between what the representation theory says and what the EDS will tell you, and they kind of weave back and forth with each other in the general argument. And I would like to remark that the argument is uniform, okay, or independent of type. So there's not one argument for the Grassmannian and another argument for the Cayley plane. It's uniform in the language of representation theory. Now, while the argument is uniform in the language of representation theory and the statement of the theorem is as well, it is not geometrically transparent what is happening in that case. So let me, as an example, state the theorem in the case of the Grassmannian in geometric language, so you can see what this rigid list really looks like.
You mentioned constants, but say, does that come in and what is it?
Yeah, it does come in because when we set up this EDS, we're actually imposing partial vanishing on part of the Moore-Cartan form. It lifts as a Pfaffian system to a frame bundle. And Lie algebra homology shows up in the EDS machinery when you prolong and mod out by normalization. So your prolonged coefficients you add have to satisfy some vanishing conditions, some compatibility. That is equivalent to being in the kernel of the homology operator, and then your ability to normalize away and take a normal form for the coefficients, that's recorded by the image.
And these homology groups, you have to compute them or they well known?
No, we had to compute them. So in the smooth case, they're well known by Costant's theorem, and Hong was able to use that really beautiful description of the cohomology for nilpotents using the Weil group combinatorics. I think in retrospect, we could have maybe reduced to that, but at the time it wasn't clear, and it was a computation. Okay, so let me give you the theorem in the case of the Grassmannian, the geometric statement of the theorem. So this is the Grassmannian of K-planes and n-space. So the first thing I want to do is rewrite our increasing sequence lambda to absorb redundancies. So U1, M1, all the way up to UT, MT. So that 0 less than or equal to mu1, so mu2, and so on. So all I've done is group together like terms, okay, and they're M1 terms of U1. Okay. So if the following three conditions are satisfied, so if Mi is at least 2 for all 1 less than I less than t, and the difference between mu I and mu I minus 1 is at least 2 for all 1 less than I less than or equal to t. And m1 should be at least 2 if mu1 is not 0. And mt should be at least 2 if mu t is less than n minus k. So check these. Then the system is rigid. The Schubert varieties are the only irreducible varieties, homologous to a multiple of your Schubert class, multiple of sigma. Okay. And you can write down other explicit geometric descriptions for the classical cases. And we'll talk about later what happens when this if fails. Okay. But just as an example, one more example, let's take a quick look at the Cayley plane. That's one of our exceptional examples. This is a 16-dimensional variety. And what I've drawn on the board is its Hasse-Poset set. So each node represents a Schubert class. The dimension of the class increases as you walk in this direction. And each node is labeled with its degree in the minimal homogeneous embedding. Some of the Schubert classes are smooth varieties themselves, and I've indicated that on the diagram. So for example, this is a maximal linear subspace. The Cayley plane contains a maximal P5 and a maximal P4, contains a smooth quadric of dimension 8, and I'll explain what the others are later. So all the way over there on the far side of the board, we have the fundamental class, and here we have our point. The rigid classes, the classes that are rigid because there are first-order obstructions to flexibility, are the following. So in particular, one thing that you can see from this picture, and that you could also dig out from the Grassmannian case, is a result of Hong's, which asserts that accepting the odd-dimensional quadric and the plane in the Lagrangian Grassmannian, any smooth Schubert variety is rigid, unless it's not a maximal, it's a non-maximal linear space. Okay. So unless it can't be for a silly topological reason I'll talk about later. All right. Okay, so you can see from this picture, and if you look at other cases, that the rigid classes, rigid by first order obstructions, are a minority. There really aren't that many of them. And we'll come back to that in a moment. That's right, because there could be higher order obstructions. But now let's address that. That's a good lead. So this is flexibility. Okay. So in the absence of first order obstructions, the Schur system is flexible. So in fact, it turns out there are no higher order obstructions. This then is a complete list of the Schur rigid classes in the Grassmannian, and likewise the red objects in the Cayley plane are a complete list. Okay, now I want to drive home a point here, which is that what this says is that there exists some integer r, positive integer, and an irreducible y, algebraic contained in X, so that y is r times the Schubert class. I don't plan to say anything about the proof. It just involves listening to the EDS. This machinery tells you how to build solutions. You just do what it tells you. One advantage of the solution, which will, the proof in this case, which won't hold in the next step, is that the argument is, again, uniform. You don't have to specialize to certain types. The representation theory language is sufficiently general not to specialize. So this brings us to the last chapter, which is superflexibility. No. Well, actually, that's not true. R turns out to be either 2, 3, or 4. But that's not transparent, and you don't want to see the computation. But. Okay. So the result with Izet states that if the Schur system is flexible, then for every positive integer r, there exists an irreducible y in x that is homologous to r times the Schubert class. Okay, this really surprised me. I was not expecting to get this much. Yeah, superflexibility. Because to someone who thinks about differential equations, having one solution, I wouldn't necessarily expect to be able to hit all the classes like this. Okay? So if r is bigger than 1, this is not going to be a Schubert variety, of course. If r is equal to 1, when you see our construction, it's a Schubert variety again. So it does not address the question. The construction itself does not address the question of whether or not the class itself has a non-trivial representative. Which are the ones that are flexible? In the picture, everything that's not circled in red. Yep, and I will take you through the argument to see that. Anything that's not circled in red is super flexible. If you're not rigid by first order abstraction, you've been doing a lot of yoga. So I wanted to tell you a bit about the constructions. They're very explicit, and one in particular is very nice. It involves teach transforms, and they're one of my favorite mathematical toys right now because they give me this illusion that I understand the geometry of the exceptional varieties. They're really nice to work with. So I'll get to that at the end. I think we'll have time. All right, so superflexibility, and the proof is essentially based on 3 constructions, so explicit construction of the representative y using one of 3 types of arguments. So first, a geometric description of S as a degeneracy loci. Okay, you've already seen that in the case of the Grassmannian. And this will work for the classical series for many of the Schubert classes in the classical series. And then a Bertini theorem type argument. And then finally, bootstrapping by teach transforms, which will help us handle the case that x is exceptional. X exceptional, so the Cayley plane and the Freudenthal variety. So let me give you an idea of how this construction works in the Grassmannian. We'll look at a simple example. The arguments in general captures the idea of the arguments in general. So this is the construction by degeneracy loci. And I'll just illustrate by example. So let's take X to be the Grassmannian of 3 planes in 6 space, and lambda to be the sequence 0, 2, 3. So in this case, S is the set of 3-dimensional subspaces with the property that it contains our fixed 1-dimensional linear subspace, and the dimension of its intersection with the 4-dimensional linear subspace is at least 2. And one way to think about this guy, this statement here, is that at least for a generic element of the Schubert variety, we have the intersection of E with P F4 is a P1 for a generic element of the variety. Something looking a lot like that will show up in a moment. Okay, so what I need to do is construct an irreducible variety Y that's homologous to any multiple that you care to give me of this Schubert variety. So you proceed as follows. You let C sitting inside the projectivization of F5 be a smooth degree equal to R curve that is disjoint from PF2. And then you let Z be the cone in that projectivization of F5. So it's a cone over the curve with vertex. That 1-dimensional linear subspace you avoided. And then let Y be the Zariski closure. The set of all 3 planes, again, such that F1 is contained in E. But now we ask that, PE intersect with Z should be a line. Okay. This is irreducible. You can check, and homologous to R times the class. And then similar arguments work in the Lagrangian, Grassmannian, the spinor variety, that type of idea. So the second construction is based on Bertini's theorem. And it's based on the following observation. So suppose that S is the only divisor, the only Schubert divisor of a second Schubert variety, S prime, and that the degree of S is equal to the degree of S prime. Then in this case, S is a hyperplane section of S prime, and Bertini tells us 2 things. First, if HR is a general hypersurface of degree equal to r, then the intersection of that hypersurface with S prime is irreducible and homologous to R times the Schubert class represented by S. And you can also use Bertini to dig a little bit about this at this question of smoothability, right? So if S prime is smooth, then so is Y for a general hypersurface, and that'll give us a smooth representative of S. So this argument applies to almost all the classes in a quadric hypersurface and all non-maximal linear subspaces in X. So let me show you at least what it takes care of in the case of the Cayley plane. So I'm looking for varieties that are of equal degree and one is contained in the other as the only divisor. So this will be flexible by Bertini, also by Bertini, also by Bertini. This guy's flexible by Bertini. Let's see, I think I'm missing some and I'll have to check in a moment. But these, of course, are all flexible by Bertini. These are flexible. This one. And that one.
So Poincare duals are not always flexible by Bertini?
Who's missed? Right, so it looks like these two are Poincare dual, right? But I can't use that Bertini argument here because these two don't have the same degree. So that is correct. Okay, so that's the Bertini argument. Okay. And then the last argument, so there's these first two arguments, constructions using degeneracy, loci descriptions, and Bertini, take care of the four classical series. And it remains to consider the Cayley plane and the Freudenthal variety. And I'll just give you an idea of how this works in the Cayley plane. This is basically a bootstrapping argument. And the idea is that for any one of these rational homogeneous varieties, it's uni-ruled by homogeneous varieties, and those uni-rulings are parametrized by other rational homogeneous varieties. So for example, the Cayley plane is uni-ruled by lines, and that uni-ruling is parametrized by another variety. So for example, let's look at this Schubert variety here. This is the Schubert variety that is swept out by all lines that pass through the origin. Okay? And it is a cone over a spinor variety. And I supposedly already know which spinor varieties have super flexible classes. And not only is this a cone, so this spinor variety over here sits inside this space. Okay? So I can take flexible subclasses in here and look at the lines swept out by that parametrization, and that will give me flexible subclasses here. And that argument takes care of the following. So let's see, what do we pick up under the Cayley plane? We pick up, we might pick up things that are also already taken care of by Bertini, but I'm not going to write that down too. There were two under the spinor variety that weren't taken, the cone over the spinor that weren't taken care of. And we pick those up with that Tietz transform. Okay. It turns out the Cayley plane is also uniruled by smooth quadrics, and that uniruling is parametrized by the dual Cayley plane. This dual Cayley plane contains a P4, and it's a maximal P4. It's basically this P4 in the dual representation, but everything underneath it is flexible. So I could look at the Schubert varieties that are swept out by these quadrics parametrized by fake representatives in the dual plane, and that will allow me to establish superflexibility here and here. So the only class I have left to establish superflexibility for is this one right here. This Schubert variety is swept out by all lines that pass through this P2. So I could take a fake representative here and look at all the Schubert variety swept out by all lines passing through that fake representative, and that is precisely what I need to get this last guy here. So that's superflexibility.
So for the Freudenthal plane as well, you have similar
Yeah,
arguments?
yeah, almost identical. But it's really great because I have no idea what the Cayley plane is. And I've thought about it a lot, and I really have no idea what it is. But I do know that all of the lines passing through a point sweep out a Schubert variety, and it's a cone over a spinor. And I am under the illusion I understand spinors and cones. So it's something to hold on to when you look at these spaces. It's really a nice way to get a bit of a grip on the exceptionals.
Well, thank you very much.
Thank you.